We're going to look at how to find the tangent plane and normal line. In these examples, we're going to start with this surface in 3D. And then in part B, we're going to do the same thing, but we'll look at this function of two variables. And in part C, we're going to look at this curve in the xy plane. And in this case, we'll be finding the tangent line and the normal line to this curve at a given point. So we'll start with finding the tangent plane. To find the equation for a plane, we need two things. We need a point that's on the plane, and we need the normal vector to the plane. Okay, we're already given the point, so the point's going to be 1, negative 2, 5. And now to find the normal vector, we're going to use the fact that we showed in class that the gradient vector is normal to any level surface. So what we want to do is rewrite this equation here as a level surface of a function of three variables. So you want to move all the variables to one side and the constants to the other. When you do that, first you can notice that this surface is just going to be a sphere with radius square root 30. And so we're trying to find a tangent plane to a point on the sphere. So a way to visualize that is this. And the tangent plane that's shown in this picture doesn't correspond exactly to our point, but it's just there to give you a visual reference. So we can think of this sphere as a level surface of a function of three variables. And to get that function of three variables, you just look here at what we have on the left-hand side of the equation. So this is going to become our function. And this particular surface is just one level surface of this function. In this case, when c is equal to 30. So now we want to find the gradient of this function. And then we're using the fact that the gradient vector is normal to the level surface. So if I want to find the normal vector to my plane, I can just evaluate the gradient vector at the point 1, negative 2, 5. And in terms of the picture, that means that I'm going to basically, okay, that's supposed to be a straight vector, but that's getting me this normal vector here that's perpendicular to my plane. Okay, so now we have the point on the plane, we have a normal vector, and so now we can come up with the equation for the plane. And this is the equation of the tangent plane. Okay, now we're going to move on to finding the normal line. So that's just going to be the line that continues to extend in the direction of this normal vector here in the picture. And so again, we need two things to find the parametric equations for a line. So to find the normal line, again, you need a point that's on the line, and then you need a vector that's pointing in the direction of the line. And we have both of those things. The point is 1, negative 2, 5, and the vector that's in the direction of the normal line is just the normal vector, which we've already found to be the gradient vector, evaluated at 1, negative 2, 5. So now we put all that together to get our parametric equations. So we have x equals, y equals, and z equals. We're going to start at the point 1, negative 2, 5. And then we want this line to move in the direction of our normal vector. And we're going to use t as the independent variable for these parametric equations. Okay, and so t goes from negative infinity to positive infinity, and that's how we trace out the whole normal line. Okay, so this is the equation for the normal line to this surface at this point. Now I want to move on to part B. So based on what we just did, I want you to take a second, put it on pause, and see if you can find the tangent plane and the normal line to this surface. Again, for the tangent plane, we just need a point on the plane. So we're given 1, 2, 6. And then we need the normal vector. The most common mistake that's done at this point is some people think, oh, then I just need to find the gradient of f at the point 1, 2, 6. And that's not what you do here. Remember, we want to look at this equation as being the level surface of a function of 3 variables. And right now, f is just a function of 2 variables. And so what you want to do is rewrite this, and just notice that we can replace f with z. And now when we have this, you want to move all your variables to one side and leave your constant on the other side. And now we can think of this as a level surface of this function of 3 variables. So I'm going to use a different, let's use g to describe this. This is g is a function of x, y, and z. And now this is going to be the level surface when g is equal to 1. Okay, now we know the gradient of g will be normal to this surface. So you want to find the gradient, and then you evaluate the gradient at the point 1, 2, 6. When you do that, you should get this for your normal vector, and then we put it both together to get the equation for the plane. Now, I want to point out that this is going to be the same plane that you get if you were to instead use linearization to get the tangent plane. So let me just show that quickly to see how you get the same thing. Remember, we can use linearization because this is written as a function of x and y, and so to get the tangent plane using linearization, we have that z is equal to L of xy, which is just, when we evaluate that, we're going to see that the z is equal to 6. The partial derivative with respect to x evaluated at 1, 2 is just going to be 2. The partial derivative with respect to y evaluated at 1, 2 is just going to be 4. Okay, and we get this for the equation of the tangent plane. And now notice, if you take this equation we have down here and you solve it for z, we're going to get the exact same thing. Okay, so either of these methods will work when you're given a function of x and y and asked to find the tangent plane. Okay, finally we just want to find the normal line, and so we have the ingredients we need. We have a point on the line and we have a vector in the direction of the line, so we put this together to get the equation for the normal line. Okay, and that's it for this example. And finally we'll look at this last one. And now we just have a curve in the xy plane, and we want to find the tangent line and the normal line to this curve. If we do a quick sketch, notice that this is the equation for an ellipse. We're going to come, it's centered at 0, 0. We're going to come out on the x-axis to square root of 18. We're going to come up on the y-axis to square root of 8 and sketch the ellipse. And then here, roughly at the point 3, 2, we want to find the equation of the normal line. So this is going to be a line that's supposed to be perpendicular, what I've drawn there. And then we want the tangent line, which is drawn here in orange. Okay, so again, we can use properties of the gradient for this. We want to think of this curve as the level curve of a function of 2 variables. So we already have our x and y, both of our variables, already on one side of the equation. And so we can think of this as a level curve of this function. So my function of x and y is going to be x squared over 18 plus y squared over 8. And my constant, so I happen to be looking at just the level curve where c is equal to 1. So I can find the gradient of f. And then we know that the gradient is going to be perpendicular to this level curve. So if I evaluate the gradient at 3, 2, it's actually going to be this vector that's right here that's perpendicular to my level curve. Okay, so to find the equation for the normal line, you have a couple options. You could do the parametric equations, and that would be similar to what we just did on the previous 2 examples. But it's actually even faster here just to write this in the point slope form of a line, and here's why. I want a line that's pointing in the direction of this vector here, and so I can get the slope directly from this vector, right? Because slope is rise over run. Well, the rise is happening from my j component, and the run is happening from my I component. So that means the slope of this line that I'm trying to draw here in blue is just going to be 1/2 divided by 1/3, or 3/2. Okay, so you have the slope that you want of the line in blue, and you have the point that it goes through. It goes through the point 3, 2. So just use the point slope form of a line. And here's the equation. Okay, now from this, because we're just looking in 2D, it's actually really easy to get the tangent line, because we know the tangent line is going to go through the same point. It goes through the point 3, 2. And now the slope, well, since these two lines are perpendicular, the slope just has to be the inverse reciprocal. So instead of being 3/2, it's going to be negative 2/3. And now you can write the equation for this line. Okay, and that summarizes different ways to find tangent planes, tangent lines, normal lines.